Hi, welcome to the Signal Pad. In this episode, we're going to review the SSA3032X from Siglent. I'm really late with this review. I apologize to Siglent for that. It's been sitting on my desk for quite some time. It's a very nice unit, 3.2 gigahertz spectrum analyzer with a built-in tracking generator, this particular one. And it's quite a lot of functionality. It's a reasonably affordable price, and I'm very eager to try it out and also to take it apart and take a look exactly how it is built. So I have lots of stuff to test. So without keeping you waiting, let's get started. And here we are on the Siglent North America website. I'm sure you're familiar with the Siglent's lineup of affordable instruments. We will be taking a look at the SSA3000X, and there's actually two different models of this, and you can compare them here. One model goes to 2.1 gigahertz and the other model goes to 3.2 gigahertz. Other than that, they're virtually identical in specification, starting at $1,600 and $3,300. Pretty affordable for a 3.2 gigahertz spectrum analyzer with all the different functionalities it provides. If you look at the firmware and software, I often look at this to see how active firmware development is, and it's pretty good. The latest one was released fairly recently, which fixes some of the bugs and so on, and the Easy Spectrum software, which is the interface for communicating and remote operation of it, and they added a couple of functionality to the EMI measurement kit there. And yeah, it's also been updated fairly recently, 2017 05 03, so I'm pretty happy with that. Not going to dwell too much on their website, but you can go over there and take a look at the exact specifications, some of the capabilities of the unit. For example, optional tracking generator, which we have on our unit. We're going to test that. Good phase noise over here. You can see pretty good displayed average noise level. So I'm quite happy with the specification. So let's not dwell on it too much. Let's take a look at the unit because I'm eager to take it apart and then start playing around with it. And here we have the Siglent SSA3032X, and it's a very nice looking instrument, big, beautiful, non-reflective 10.1 inch 1024 by 600 resolution screen, and it's completely matte finish. It really is. I wish everybody did that using these type of screens because it looks so much nicer in the lab. Let's go and turn it on, see how long it takes to boot as I'm describing it. So obviously we have USB port in the front. We have a headphone jack for listening to demodulated signals because it does have AM and FM demodulation capabilities built into it. Tracking generator coming out. RF input going in, both of them type N. Nothing unusual there. Nice big keys on the keypad, logical placement for them, very classic distribution. Basically, it's very similar to a keysight instrument, and that way you have this familiarity with it if you're using those. Nice rotation knob there. It feels reasonably good. And yeah, a whole bunch of other buttons that you would normally access there. It has an auto tune button. I don't know any professional who ever uses an auto tune button, but anyway, it's there if you want to find a tone that's very dominant quickly or something like that. But there are measurement buttons. We will go through that. Very nice, pretty straightforward. As you saw how long it took to boot, it's a pretty quick instrument, and it boots quickly and is ready to go right away. Quite happy with that. And at the back of the unit, nothing unusual. Obviously AC line going in here, and we got a couple of connectors here. We have the trigger in, we have the reference out, reference in, and LAN and USB standard, which is great. We got a lock there. Yeah, it looks good. This one was made in April of 2016 and looks good. I have to say it's a very nice modern looking instrument. I have no problem with its design. It's got a nice big handle. It's a nice weight, fairly quiet. It could be a little bit more quiet, but not bad. I'm eager to try it out and take it apart and see what's going on inside. Alright, let's take a look inside the unit. Now I've already taken the back off. There's nothing exciting about that part of this assembly, so I did it in advance. And here you can see the cage that protects everything. This of course performs several tasks. It's an electrical protection from stuff getting in and out. It provides a nice grounded chassis, mechanical stability, and so on. And you can see the AC line directly going in there, and then from underneath feeds into underneath this chassis cage, which the power supply is mounted. So this design technique is also pretty common. The power supply will be removed at the same time as the chassis. Now the power supply is going to have its own protection, I will show you, and this totally separates that portion of the circuit from the rest, and this is quite nice. And all the BNC connectors will be have been screwed onto the chassis, and this provides mechanical protection for these guys as well. So I've already taken all the screws out. The chassis seems to be in pretty good shape, pretty good condition, so no complaints there. And here is the inside. So just going to quickly show you. As I was mentioning, you can see the power supply completely shielded over here. There's a fan in there which then plugs directly onto the board underneath. And in terms of Thermal, it's not bad. We got the airflow across the power supply, and some of the components over here, there are holes strategically placed in different places. The holes on the power supply are really quite tiny, so I'm not sure how much airflow you would get with such small tiny holes on this over here, but anyway, they've definitely put a fan there. You can see everything properly connected. Over here, sorry, let me see if I can get this into refocus. There it is, you can see the different lines going in, but nothing unusual, and the power supply output right there. So I'm going to put this aside. We're not going to dwell too much on that power supply design and so on. Only if necessary, we'll dig into it. And here's the board, and I mean, it looks beautiful, as we've seen with a lot of these later Chinese models of these instruments. They're basically indistinguishable when you first look at them from any of the other high-end instruments. They've really nailed down this design. It looks really nice, very clean. Everything is pretty nicely laid out. So we can see a ribbon here. Every time I see a ribbon cable, I would like to see them taped down. But again, it's not a big deal. This is obviously the LCD connector and a few other connectors between various boards here. And these connectors will carry DC, digital configuration lines, and so on. We'll take a close look at these components in just a second there. You can see USB, Ethernet, the 3 BNCs. We got our buzzer over there that makes noise and various commands and so on. A few interface lines for serial and also for programming and configuration. Our FPGA over there in there. A couple of unpopulated components. Interesting. There's some memory like this one is unpopulated. And we also have another component there that's also unpopulated, and a bunch of other things. I wonder what it's used for. I see a room for what appears to be a crystal. So it's interesting to see that. And here's a micro SD card, actually, that's not accessible from the outside. Perhaps I'm booting and loading some firmware onto it. Other than that, looks good. So now we can see clearly 3 different cages in here, and we're going to take these off because I want to see what's underneath it. Now, by the proximity of the RF connectors from the front of the instrument, the tracking generator would line up here, somewhere around here, and the RF input would line up somewhere around here. So this is clearly the RF deck. First, second, or maybe third converter will all be in this portion, and this is a tracking generator, so this will be responsible for generating the obviously the signal coming out from the tracking generator, and this is separated from the other one so that you don't have contamination from one onto the other. This would be very bad. If you turn on the tracking generator and you actually get leakage into the RF input, it will totally remove the dynamic range of the tracking generator during measurement. So we will test that also. And over here seems to be the last section. Now, this is clearly our digital board. So by the fact that we have this over here, most likely the final IF stage or the IF digitizer is handled over here. Seems to be a signal coming back, perhaps some kind of a reference. There is some other also nodes going back and forth, maybe references as well as the LO signals going in different locations. I don't know, that looks really nice. I mean, there's going to be not much on the other side, so I'm not going to bother with taking that part out. But a lot of DC stuff over here. I'm going to dig out the part number of these just so that we can see what it looks like when I take this cage off. And we'll take a close look at it. But so far, I mean, it looks good. I have no complaints. All right, here we go. Let's take a look at this step by step. I've already removed the other RF sections from here, and this one I kept into the case. It's actually come out quite easily, so we can take a look at them in isolation. So here is our main digital portion. As I mentioned, over here is where all the DC-DC converters and power management takes place. Nothing really unusual going on. The power comes directly through here. By the proximity of the LCD to the FPGA, we can see that it's driven by the FPGA directly there. Now, right next to the Spartan 6 FPGA, there is an ARM processor. This is a Texas Instruments Citara processor. This is a Cortex A8 32-bit RISC processor. Very common technique to combine a RISC processor and an FPGA on a lot of these instruments, including oscilloscopes, where the ARM processor is responsible for running the application in the background, and FPGA handles the data coming from the A to D converters, handles all the communication with the peripherals, the synthesizers, the variable gain amplifiers, the switches. Everything is going to be controlled by the Spartan FPGA there, so which you can, of course, configure and keep changing as needs come up. And the combination will then drive the whole instrument. So nothing unusual. There's some flash memory, some RAM, and of course the network controller, USB controller. Very quite a common architecture. Now, once we get up here, things are a little bit interesting. And this is where, as I mentioned earlier, the digital IF portion is. And I was right. It's indeed handling the digital portion as well as reference management. So there's a 10 megahertz crystal over here, and the 10 megahertz in and out coming from the BNC connectors will also be handled in this section over here. Nothing unusual over here. We have an analog devices part. And this is an ADF4001, and this is a 200 megahertz PLL, so it manages phase lock looping for the reference to various other frequencies which may be needed by the A to D converter, as well as some of the other components which may be on the RF deck and the tracking generator. And over here we have where the clock would leave the chip. There seems to be some high power clock driver IC over here. So this whole portion is the reference management. Now here is the IF management. This is the digital IF backend, and you can see the IF coming over here. The very first thing is a National Semiconductor digital VGA and a 16-bit driver. And by 16-bit driver, I mean that this is designed to drive ADCs up to 16 bits, so it has a spurious dynamic range and a total harmonic distortion which suits, and of course the noise which suits a 16-bit A to D converter. Now this particular instrument doesn't use a 16-bit A to D converter. It uses an Analog Devices 65 megasamples per second 12-bit A to D converter. So this is quite nice combination here, really not going to be limited by the digital VGA. And of course the digital VGA also handles a signal full-scale management before the A to D converter, so that you can have the maximum dynamic range from the A to D converter. Also a very common architecture, the dual VGA is going to have to get feedback from the output of the A to D converter through the Aspiron FPGA most likely, and is in continuous loop to keep the maximum dynamic range. And if you overload, of course, then you will catch the overload condition, and we will check that. So other than that, really nothing unusual, very straightforward architecture from this point of view. And if I look up a little bit here, the management of the buttons on the front panel is of course all handled by the FPGA as well. So as you can see, very nice, very clean design, and the components are predictable. The architecture is pretty straightforward, and the performance should be good. They're using quite good components. So let's go ahead and take a look at some of the other sections. All right, let's take a look at the RF board here. It looks really nice, very clean design, good soldering and everything, no complaints there. I've taken a quick look at it just to kind of reverse engineer its architecture, and I have some ideas and some thoughts that I want to share with you here. So the input coming in goes through a very familiar input network. Now we've seen this input network quite a few times in different instruments that I've opened, different spectrum analyzers that are open, and it consists of a series of solid-state switches, solid-state step attenuators, as well as some resistive attenuators and some preamplifiers. And this combination gives you all of the dynamic range switching that you would expect from a spectrum analyzer, so that you can get different reference levels and process different input signals without overwhelming the mixer. So this is a very common technique there. After that, we have a filter and a mixer. And it looks to me that this mixer is using an up conversion. So they actually convert the 0 to 3 gigahertz signal to a higher frequency, about twice as much, before they down convert it back and process it and eventually reach a final IF. This allows them to use a sliding LO in order to sweep the LO frequencies within the range they want. So instead of sweeping the LO within 0 to 3, they sweep it at a much higher frequency, and that has some advantages in the frequency planning they have in the overall architecture of this instrument. So pretty cool and pretty straightforward. And if you look over here, this Z communication VCO over here is the core VCO for the instrument, and you can see that there's a coupler here. So they take the output of the VCO, they couple some of it back, and they put it into a Hittite Analog Devices PLL, and that synthesizer then closes the loop between it, and so you now have a locked VCO that you can set the frequency between 2 to 4 gigahertz. That's the range of this Z communication VCO. The output of that goes through a frequency doubler. So now this doubled frequency is going to have quite a bit of harmonic. Not only is it going to have all the intermodulation harmonics of the Z communication VCO because of its limited total harmonic distortion, it's going to also have the fundamental feed through and the fourth harmonic and so on coming out. So they need to filter this, and they pass this through a switched filter bank. You can see some solid state switches here, and they choose 3 different filter banks depending on the frequency that they're using in order to get a nice clean CW tone coming out. And that's really critical because harmonics of this VCO, you don't want to feed that to the mixer up there, because if you do, you're going to have multiple down conversions on top of each other and you're going to ruin your spectrum. So they need a very nice clean signal there. So you can see the output of that after it's filtered, goes through some butterfly stubs, and then eventually reach the mixer there, and the up converter signal comes out of the mixer. But before they do that, they also couple it out with another coupler there, and they take that signal all the way over here and they pass it to this connector. And this then becomes the LO for the tracking generator. This ensures that you have this coherence, or I should say a frequency locked version of the LO passed to the tracking generator, so that when you use a tracking generator, you can actually get a frequency tuned and frequency locked measurement between the sweeping of the input of the spectrum analyzer as well as the tracking generator. So very common technique. Again, you need a locked LO to pass through a tracking generator, otherwise you can't do that type of measurement. And the output of that then is filtered again, most likely getting rid of all the out-of-band signals that you don't want to have to process by your second mixer there. So now we have our second mixer over here. Now this down-converted mixer is going to need its own LO, and that LO comes from another synthesizer there. And it's interesting to see that this synthesizer has a forward path, obviously, again filtered before it goes to the mixer, but it also has a coupled path which goes through a divider, and that divider drives another mixer, so this will be your second IF at that point, and the input of that is coming from the down-converted signal of the first mixer over here through some SAW filters over here, and then processed once again before it becomes a final IF and goes out of that connector there. So this is kind of my very quick reverse engineering of it, just looking at it for a couple of minutes, and I think it's pretty accurate. If you see any issues, if you have any questions, we can investigate further, but I think it's pretty straightforward. And then we have some Altera Max 5, I believe, or they call it Max V, I'm not sure. Probably yes, the Max series are flash-based FPGAs, some glue logic to close everything together, program the synthesizers and create a nice straightforward interface to the digital board. It's very nice, very clean. There's really nothing on the other side. There's no point looking at it. But yeah, pretty happy. Looks pretty nice. So let's go and take a look at now the tracking generator, and we can follow where this signal goes. And just keep in mind then we have two different synthesizers there with the dividers and the multipliers and the filters. You can get a rough idea of how it works. So pretty cool. Let's move on. And here's the tracking generator board. It looks to be quite similar to the one we saw earlier. So there is over here, we have a reference coming in for the synthesizer over here. The output of that synthesizer is then mixed with the LO that is fed from the other board and then filtered again and then passed to this. So this LO coming out of here will then be between DC to 3 gigahertz as we would expect, which then matches the sweep center frequency of the main spectrum analyzer. So again, using a very similar architecture with a mixer, having another synthesizer there. So they have quite a few Hittite and Analog Devices parts in here. Nice to see high quality components definitely used here, nothing unusual. And yeah, so now we can put it back together and try it out. Now that we see kind of the frequency planning, we can try and stress test it in some of the places where we feel it might be weak. So for example, the harmonic purity of the LO coming out of here from the tracking generator would be something to look at. Injecting high power frequencies outside of the frequency operation of the instrument would be another thing to try out. And I also want to see how it behaves over load conditions and so on. And then we can do some experiments with it. So let's go ahead. I'm going to put it all back together. Hopefully it will still work. And then we go from there. All right, to start off, let's do something really straightforward. I'm going to be providing the signal using my Agilent EXG, and then I'm passing that through an Anritsu programmable mechanical attenuator, and then finally putting it into the Siglent spectrum analyzer. Now, the reason I do this is because I want to make sure that I don't change the attenuation level or the signal level coming from the synthesizer itself, so that our total harmonic distortion and our intermodulation products are not going to be affected by the difference amplitude that's coming out of the synthesizer. This way we're going to be applying a mechanical attenuator there, therefore our relative signals will stay constant. This is very important, otherwise as you change in the signal amplitude here, you don't know if the additional tones, if they're going to be present, are coming because of the linearity constraint of the EXG or because of the linearity constraints of the signal spectrum analyzer. This is why it's set up this way. So let's go ahead, take a close look in there. Now it's powered on and we can see how it behaves. All right, let's do some measurements. So I have set my synthesizer to 1 gigahertz and the output at 20 dBm. And I have set the Anritsu programmable attenuator to 20 dB of attenuation. This means that I should expect to receive a signal of about 0 dBm to the input of the spectrum analyzer. And right now it's in preset mode, so it's default startup condition. Let's go and enable DRF. And there it is, quite nice. We can see our fundamental tone very clearly there. We can see our second harmonic. Now this second harmonic is coming from the synthesizer itself because it's generating a 20 dBm signal, which is quite large. And therefore it's going to have some THD limitation as a result of that. But it's actually still pretty good if you look at how many 10 dB divisions these are far apart. It looks like about 40 dB of difference. So it's quite good. We can do a peak search. And indeed, we can see we have a amplitude of minus 2 dBm. There's some losses in the cables and so on, some insertion loss in the attenuator, but it seems pretty reasonable. So no problems there whatsoever. We can go ahead and go to the marker menu. We can create another marker. We can do the peak on that marker, and we can check the next peak, and therefore we have now both peaks there. And we can even turn the peak table on if you really wanted to see, and we can clearly see our fundamental peak at -2 dBm and the second harmonic sitting at 2 gigahertz and -44 dBm, more than 42 dB of separation between the two tones. Quite nice. So let me go ahead and turn this off so we can see nicely our two tones. So I'm going to go and reduce the attenuation from the Anritsu. Now remember, this is a 0 dB reference. So the 0 dB reference has some input attenuation by default. So if I go under the amplitude setting over here, you can see that the instrument is selecting an attenuation of 20 dB by default, and the preamp is turned off. So let's go ahead and reduce the attenuation. So there is now we've got 5 dB down. Let me go under marker again. So we can see the first marker, so we can see the amplitude, and look, it's sitting at 3 dBm, so it's now above the reference. Now it's normal to be able to do measurements above the reference a little bit. It's not an issue, but at some point you're going to run into some linearity limitations of the instrument, and the instrument would have to warn you that you're doing an overload condition. So let's keep going and see what happens. So now we are at 10 dB attenuation, and you can see that the signal is 8 dBm above. So it's still showing the correct value, but you can see it's starting to generate some unwanted tones there. Now it's not warning me yet that this is being overloaded. So you have to be careful that you would notice that you are in an overload condition, and that you would know that this tone is not real. It's not coming from the synthesizer, it's coming from the instrument itself. Now I can continue on this. So now we are really pushing it. We are now 13 dBm above the reference, and you can see this tone has grown quite a bit, quite significantly, and our second harmonic is now quite large as well. But let me see if the difference has changed or not. We can go under the marker. I can turn the marker table on. And what are we looking at? We're looking at, yes, you can see that the difference is about the same actually. No, it's still good. It's still preserving THT, so that's not an issue. It's because it's sweeping. So when it reaches the second tone there, it's already filtering the first one. So that's why it works quite nicely like this. Let's go ahead and turn this off. But this other tone there is certainly a linearity problem from some of the IF stages. It's not clear which one. But if I keep going, you can see there it is. And now at this point it's saying warning ADC overload, because it knows that the final ADC is overloaded. So let me increase that because it's very annoying. But as you can see, the final ADC being overloaded, even before that, you have some IF nonlinearities, and that's what you're seeing. So you just have to be careful. It's a minor issue, but it's something to definitely look out for. So if you see some unwanted signal, you know why. You just have to have an eye out whether any measurement of any signal is above the reference by a lot. And sometimes some spectrum analyzers actually don't show you that the signal is exceeded the reference. They'll just compress, and that they don't even tell you they're doing that, and that would be bad. So in this one, it's not such a big problem. It's detectable, so it's we can work around it. And let's take a very quick look at the shape of the phase noise of the SSA3032X. Now, I'm using the EXG, which is very clean, so the shape of the phase noise is going to be dominated by the phase noise limitations of the SSA. So it should be pretty interesting to see. Right now, we're looking at a 1 gigahertz signal again. Let's go ahead and set the center frequency to 1 gigahertz over here. And let's go ahead and reduce the span. If I can reach around, it's an awkward angle here. There we go. We can look at a 10 megahertz span there, not bad. And let's reduce the resolution bandwidth. Sorry, that noise that you're hearing is my spectrum analyzer booting up. So let's go ahead. There it is. Not bad. You can see it's fairly clean, and it's very classic response from one of those Hittite synthesizers that's inside there. So looks good, and I'm not going to bother measuring exactly the the response and so on, because it's going to match the datasheet anyway. So I just wanted to show you that it indeed has a nice symmetric, no spurs near the carrier, which is great. Let's go ahead and try it at a higher frequency there. So I'm going to set the frequency to 3 gigahertz, like so, and we can change the frequency from 1 gigahertz to 3 gigahertz. We should be able to see a very similar response there. And there it is. You can see the noise floor is a little bit higher because the noise figure of the instrument is higher at 3 gigahertz. But so you're running into the displayed average noise level of the instrument here. Otherwise, this would go further down because it just simply doesn't have enough dynamic range to show you that. But it looks pretty good. And we can turn on averaging and detector averaging and so on, so you can get a better idea. But really, it's very straightforward. Nothing unusual. So quite happy with its basic response there. Let's go ahead and take a look and see how good the tracking generator output quality is. So whether you can use it as a standalone synthesizer. And then we can do some actual measurements of a couple of different circuits, which would be pretty fun. Let me just go ahead and set up that. All right, so here's our setup initially. I'm doing something very simple. I'm taking the output I'm taking the input of the spectrum analyzer and I'm connecting it to the input of another spectrum analyzer. And this is to see if there is any feedback coming out of the RF input, if there is any leakage of the internal LO signals coming out of the spectrum analyzer, which can interfere with a very sensitive measurement you might be doing. This can happen if there's not enough isolation, or if the LO system internally is not well designed. So here we're looking from 0 gigahertz or 0 hertz all the way up to, let's look at all the way up to maybe 7 gigahertz here, because we know the LO frequencies are higher. And you can see that there's occasionally, when it sweeps, some higher frequencies, and these are because, as I mentioned, our LOs are quite high internally. We have an up conversion, so there's a little tiny bit of leakage coming out, but it's really nothing. So I'm quite happy with that. It does a pretty good job. Now, right now, the tracking generator is disabled, so let me go ahead and enable the tracking generator, and I'm going to set the value of the tracking generator to 0 dBm, so very high level, as high as it goes. I'm going to turn it on. And let's see if there is any difference. And no, very good. It definitely has no effect. And even though the tracking generator is actually unterminated, you can see it is completely unterminated. So this is the worst condition for it. And you can see that it doesn't have any reverse leakage into its input. So I'm quite happy with that. We can go ahead and now measure the actual tracking generator source coming out. And it's obviously going to be sweeping right now. We're going to see it jump all over the place. And that is normal. There it is. So we can go ahead and stop it at a couple of different frequencies and see the quality of the signal. So there's no point filming the screen of the SSA there, so I'm going to just focus on this one. I'll tell you what I'm setting it to, so we can see the quality of the tracking generator. All right, let's take a look here. So let's set the frequency to be, let's do actually a center frequency of 1 gigahertz, and let's do a 0 span. There it is. So with the 0 span, we're going to have a 1 gigahertz signal coming out. And as you can see, yes, it is a 1 gigahertz signal coming out. Indeed, if I do a peak search over here, there's a 1 gigahertz signal, and its amplitude is just over 0 dBm. So it's reasonably accurate. It's obviously a little bit higher than it claims to be. But that's okay, because you normalize it for most measurements. It doesn't matter. And it's okay. I mean, it's got quite a bit of other tones there. The biggest tone is about 20, 23, 24 dB down. It's okay. You can still use it as a synthesizer. Just keep in mind that it's going to have some impurities in it. Normally, I don't have much problem with harmonics. What I generally don't like are these other tones that are very close, because they're unpredictable and they can cause a lot of intermodulation tones. But from some of the other tracking generators that I've seen in the market, this is actually pretty good. So let's go ahead and change the frequency. That's a 1 gigahertz. We can do 2 gigahertz. You can see 2 gigahertz there. Now the amplitude seems to be a little bit larger still. Ooh, 2 dBm. Yep, it's definitely putting out more power than it says it is, which can be quite good if you're measuring some passive networks. You won't run into dynamic range limitation. You want it to be accurate, so you know what you're expecting. It's supposed to be 0 dBm right now. And let's see at 3 gigahertz. What do we get at 3 gigahertz, which is the higher frequency? And there it is. X3 gigahertz is actually the cleanest, because most of it is outside of the band, so you won't see it. Remember, I'm sweeping all the way to 7 gigs, so we will see harmonic outside of that. So yeah, 3 gigahertz, it's a pretty good synthesizer coming out. You can see it's putting at -1 dBm there. The harmonic, is just under almost 40 dB down. Not bad. So yeah, quite good. I would say it is a reasonable tracking generator. Let's go very low frequency. I'll say 100 megahertz. That's a tough one, but yeah, you can see all the harmonics coming out. So it's actually quite pure at 100 megahertz. Only has got harmonics in it, and the amplitude is fairly accurate. Yeah, not bad. At 500 megahertz, not bad. And at 1 gigahertz seems to be actually the worst condition. Yeah, it gets pretty bad at around 1 gigahertz. Let me try 1.5 gigahertz. And yeah, you can see there's some harmonic out there, but otherwise, honestly, not bad compared to considering the price of the instrument. I would say this is pretty good. It's usable for a lot of applications. You just have to be careful about some of the harmonics. Nice, not bad. Let's take a look at the phase noise response of it a little bit, just for sake of completion there. So let's say, what are we looking at here? Let's say 1.5 gigahertz. So we can set the center frequency to 1.5 gigahertz. We can reduce our span there. And there it is. You can see how fast this instrument sweeps. Of course, the EXA is going to do that, but it's orders of magnitude more expensive. Let's see what I was going to do. I was going to use the bandwidth. Yeah, pretty good, I would say. Look at that. Nice. You can see the skirt continue going down, because this instrument has a much lower displayed average noise level at 1 kilohertz resolution bandwidth there. Pretty good, I would say. It's a success. So now that we have an idea of what to expect from different ports and some of these basic measurements, let's measure something that we don't know. So I have this interesting antenna board I want to measure. Let's go ahead and try it out. So the first thing I like to characterize is this antenna and diplexer module. So this is a dual polarization antenna. It's supposed to work around 700, 800 megahertz. So what we don't exactly know, so we want to find out. And the top of it is the antenna module, two polarization, and the bottom is diplexer. And I can separate these from each other. And there it is. So now we have two separate modules. Let's look at the diplexer here. Not to be mistaken with the duplexer. This is a diplexer, so it separates in frequency two different polarization channels on the same port. So here we have TXRX1, here we have TXRX2, and at the back of it, these will be separated into four different ports. So there is TX1, there's TX2, there's RX1, and there's RX2, or the other way around. So we can measure the response between the various ports of this diplexer and see how good the isolation is, how good channel separations are, how much isolation you get between RX and TX channels versus how much you get between the two polarization channels. Now, between the two polarization channels, I expect to have excellent isolation because there are separate chambers within this that are created. But we want to measure that, so we have to obviously use the tracking generator functionality to figure out the frequency response of this, and I'm interested to see how easy is it to use the SSA to plot them on top of each other and get some quick measurements, reliable measurements that you can print out later and use for system characterization. So that's the first part. And the second part is I want to also measure the antenna itself and see if we can get at least a reasonable idea of the center frequency of this antenna there. So obviously the antenna is going to have two ports at the back of it, one for each polarization, and the TX and RX obviously going through the same antenna ports. And if I look inside, you can get an idea of the architecture of it. You can clearly see the X in the middle, very characteristic of this type of antennas, and there's a reflector at the top of it. So there it is. Let's go ahead and start measuring. Now, it's probably easier to start measuring the diplexer first before we measure the antenna because we don't need a coupler for that, but we should be able to get a reasonably good idea of how to do this. Let's go and see how easy it is to configure the instrument for this measurement and figure out how this thing works. All right, let's do some calibration here. Now, the connectors on this diplexer are these special pins, and I do have those pins, and I made some cables out of them, but unfortunately I don't have a through. So you can see I made some cables myself here with those pins at the end and SMA termination on the other side. But I can't connect two of these things together because I don't have a through. So we're going to have to make a small approximation when we do our normalization with the tracking generator. So I have two cables here coming out of the instrument, and we're going to put a through between them, and then when we normalize, the measurement plane would be at the edge of these connectors, or more precisely in the middle of the through. And unfortunately, we have to then take the response of these cables as being part of the response of the diplexer. But that's okay. For our purposes, it doesn't matter. So let's go ahead and turn on the tracking generator. And we can go ahead and set the power to 0 dBm because this is a passive device. We can put as much power as we want in this particular case. And let's go ahead and connect these guys together, and then we're going to turn on the tracking generator and see the raw response. Now the raw response obviously is going to show the variations in the tracking generator power, and there we go. So we're connected, so we can put that down and go ahead and enable this, turn it on, and there it is. We're at very, very top of the page there, and that's because we're a little bit over the reference, because as you saw, the power coming from the tracking generator in some cases was above 0 dBm. So let's go ahead and turn on the normalization, and there it is. It's now normalized, and let's put the reference value at 50% of the page. There it is. So we are perfectly normalized in the center of the page. You can see we are at 10 dB per division, and yeah, everything looks pretty good. Nothing unusual there. So we can go ahead and now disconnect this, and then we will see that the curve will drop down well below -50. And maybe I should change the reference and not put it at 50%. Let's put it at 75% or something like that. There it is, so we can actually see the bottom. So here we go. This is basically the noise floor of our instrument at the moment with the current resolution bandwidth. And we can even do maybe a little bit more just for the sake of being able to reduce the resolution bandwidth if you want to. There you go. It looks pretty good. Very straightforward. Obviously, a lot of instruments do it this way, and no problems there. Now we can go ahead and connector cables. And oh, one of my throughs came off over here. So obviously, technically speaking, I should be using a torque wrench and, you know, tighten all of these, but for our purposes, it's fine. This is an SMA, not as sensitive as doing measurements, of course, in the tens of gigahertz. We're only measuring up to 3 gigahertz here. So now that we're connecting all of these guys, perfect, there it is. So now we have 2 of these cables. If I bring them very close to each other and kind of almost touching them, you can see that they radiate into each other, and we can get some response and showing that indeed these connectors have some signal on them. Now that if I had it through and I would connect them perfectly together, then we would only see the response of these cables that I added. But we don't have that, and that's okay. So let's go ahead and see what we want to measure. Well, there's a couple of different places we can measure. Let's flip this guy. So we have RX1 here at the very top, and we have RX2 there, and then we have TX1 and TX2. And on the other side, we have obviously the RX-TX1 and RX-TX2. So I'm interested in measuring the response between the RX-TX1 to each of the ports of the RX-TX on the other side, and that will give us the diplexer response. And we can see exactly what frequency response we have, what channelization we have, and how the frequencies are separated within the diplexer. So I have to take these pins out, and I'll be right back. All right, let's go measure this now. And I removed the cables. I re-normalized with shorter cables that were kind of getting in the way. But anyway, same principle. So let's measure this guy. Now, I'm going to connect the tracking generator to the antenna port of the diplexer. This is a reciprocal network, so it doesn't really matter. But just for sake of consistency, here is our tracking generator connected to the antenna port. There you go, it clicks in nicely. And let's measure the receive channel. So the receive channel, RX1 in this case, is sitting at the top right over there. So I can go ahead and plug this one in there if I can reach it. And there it is, plugged in. And let's move it a little bit out of the way and check it out. Look at that nice response over here. I can do a peak search with a marker, and you can see our channel at 780 megahertz. So it looks pretty good. Now we can perhaps center it so we can see it better. Now let's reduce the span a little bit. And check it out, nice beautiful response from the receiver on the diplexer, and you can clearly see a nice flat region in there, which is our channel. We got good rejection. If I do a peak search again here, we can see it around 785 megahertz. We can see the width of the channel there, and we have about 40 dB of rejection. Now, one thing to keep in mind is that I did this normalization on the full scale, so the number of points I have available to me is obviously going to be coarse in frequency steps. And when you zoom in, your normalization isn't exactly accurate. You're going to have to do some interpolation. So just keep that in mind when you do this. So, for example, I'm going to move this to the right a little bit, and if you pay close attention, you can see the shape of the response at the top changes ever so slightly as I move it, even though it shouldn't do that. This is just because of my normalization. Once you discover your center frequency, you want to renormalize so you have a good resolution in your normalization function. But for our purposes, it's good enough. Now, let me put this back over here. Let's actually set it to 780 megahertz, the marker exactly in there. So somewhere in the middle of the channel. There we go. We have minus 2.3 dB or so of loss. And remember that loss is mostly coming from our cables over here and the connectors to the diplexer. Even though I wiggle this, I don't see any change there. So it's got a fairly good connection to the diplexer. Now I want to measure the TX channel. Obviously, I don't want to lose this waveform. So we can keep this waveform on the screen while we switch. And there's a couple of different ways to do that. The easiest way is to just create a new trace. So let's go under our trace menu. And actually, let me zoom in over here. As I promised, I forgot. So we can take a quick look at what's going on here. So under trace menu, we're obviously on trace A. We can do a max hold, min hold, view and blank. By view, they really mean hold. That's what it should be called. So if I put it on view, it will hold this waveform for me and it wouldn't update it anymore. So I can go ahead and create a trace B now, and I can do a clear write on trace B. So now we have a trace B which is active and dynamically changing, and this time trace B is going to be right on top of trace A, obviously because I haven't made any changes in my measurement. So let's go ahead and make some changes to the measurement, and let's remove that from the TX port, from the RX port, and connect it to the TX port. There we go. So once I remove that, we can see that obviously the purple line goes down, trace B goes down. Where is TX1 anyway? There it is. TX1 is down here. So I can plug into the TX1 and check it out. This is beautiful. This is a really good measurement, and you can clearly see the diplexer's response there. Fantastic. Let me move this a little bit more out of the way. And take a look. Here is our RX channel in the FDD diplexer form. Then there is the other one. We can see the TX channel. The TX channel is a little bit wider, and it's got a slower roll-off there, but they're quite separate from each other. And look at the overlap here. First, let me do some markers so we can get an idea. So I'm going to click on marker. Now marker 2, I'm going to select trace B from marker 2. And now I'm going to do a peak search again. And now we have both of these markers next to each other. By the way, see how easy it is to navigate the menus? If you're familiar with the Keysight, for example, navigation menu of spectrum analyzers, you would fit right in. This is exactly the same structure, very intuitive and easy. All the variables, everything available here. I wish they weren't wasting so much space here on the screen there. But anyway, that's a minor issue. If they moved it a little bit to the right, you could get more space there. So now we have both of these. We can obviously turn on the tables on, and you can see that it will tell us the different markers and where they are and so on. So this is actually measuring the peaks. That's not what I wanted to do. My apologies. What I wanted to do was the marker table. There it is. There's our marker table. So we have trace A and trace B. We have marker 1 and marker 2, and we have the two different center frequencies roughly of the two channels. Let's go and turn that back off there. And we can see that we have quite a bit of rejection. This point over here is around 60 dB. So that means that the response of the TX and the RX, the two channels, have at least about a 60 dB of isolation between them. And this is very good, and this is necessary if you want to obviously do any reasonable FDD type of radio without overwhelming the receiver when the transmitter is running. So this is quite normal and is pretty good for a diplexer. Now we can also measure the response between the TX and the RX on the same polarization, just to see how much isolation we have directly on those ports. And that's pretty easy to do as well. And I'm going to go ahead and disconnect this from the antenna port. Let's go ahead and do that. I'm going to plug this out. There we go. And I have to find a way. Let me put this flat and plug this into the RX1 port. And this is the RX1 port. There it is, RX1 and TX1. Now we're looking at the isolation between the two of them. Now this is so low that it's difficult to see. So let's go ahead and let's get rid of trace, the second trace. Let's go to this one, do a clear right on this trace, and let's reduce the resolution bandwidth over here. And there we go. Once the resolution bandwidth is reduced, now you can begin to see some limited isolation between the TX and RX. But as you can see, it's below 60 dB, which is exactly what we expected it to be. So it has excellent isolation, and it's not going to have an issue, but we could already see that when we were measuring RX2 antenna and TX2 antenna. Now, this is in the same polarization. I could also measure across two polarization, and I would expect that to be well below the noise floor of this instrument, because these are two different microwave cavity chambers. You're not going to have any interactions between them, but we can try it. Let's look at between RX1 and RX2. Plug that in, and there we go. If I can plug it in properly. Oh, you know what? Actually, I do see something. I see a tiny amount. Interesting. I wasn't expecting anything at all, but no, the noise floor of this instrument is low enough. We are seeing some around minus 70 dB. Pretty interesting. And if I unplug that, you can see that indeed this is real. You can see, if I plug it in, that there is some limited isolation. That's very interesting. I wasn't expecting that. Let's try the between the two RX ports. Oh, I should say between the two TX ports. Maybe that one's better. Let's see if you see anything here. Yeah, between the TX ports, it's really small. But yeah, between the RX ports, there's a little bit of isolation issue there. Fascinating. Anyway, so there it is. Now you can see exactly how we can completely characterize this diplexer by using the tracking generator functionality of the SSA. And you can see how easy it is to do this, because it has got a nice GUI, got good dynamic range. It puts out a reasonable amount of power from the tracking generator, allows us to make these extremely low signal level measurements fairly easily. So now the question is, how do we measure the antenna? Well, for the antenna, we're going to need a directional coupler. And I actually have a directional coupler over here. And we can use that directional coupler to characterize, or to, I should say, to normalize the instrument. And then by normalizing it, we can measure the return loss of the antenna. And then we can see the interactions of the S11, or the magnitude of the return loss of the antenna, on where various objects are in front of the antenna. So it should be pretty cool to take a look at that. Let's get that going. All right, let's do some normalization with this directional coupler here. So I have the directional coupler, one side of it connected to the tracking generator output, and the through path of the coupler is right now unconnected, and the reflected path is connected to the RF input. Now this is a 15 dB coupler, so you're going to get 15 dB of attenuation, even of all of the energies reflected back through the through port. And we can try that out and see if that works. Go ahead and turn on the tracking generator and check it out. I can do a peak search. We're at about minus 16 dBm, which is very consistent because we have an open port there. So all the energy is being reflected back, and then 15 dB attenuation and then to the RF input. So this is the highest level of signal we would get at the RF input in the case of a full reflection on a passive network. I can go ahead and connect a termination to it, and if I connect a termination to it, you will see that the waveform will drop. That's because all the energy is of course now absorbed into the load, and then we're at the noise basically at the minimum value that we could possibly measure in this configuration. It doesn't have perfect isolation and so on, but it is good enough for our purposes. So since we're going to be using one of the cables that I made for this job, it's good to connect that before we do our normalization. So let's go ahead and do this. And by the way, when you're turning one of these, the cable shouldn't be rotating again. Not being very careful here, but you should take care when you do this. So there it is. This is my cable, and I'm going to just rest it gently on the table there. And this is the waveform we need to normalize now. I can go ahead on the tracking generator, turn the normalization on, and set it to a reference of, let's say, 25%. There we go. Oh, did I normalize it? I did, didn't I? Oh, I think I made a mistake. That's not what I wanted to do. I wanted to press normalize. There is our normalization. There it is. Perfect. All right. There it goes. Looks good. So now we are sitting there at a perfect reflection point, and is measuring. If I do a peak search over here, 0 dB. Great. Looks good. So now let's go ahead and connect it to our antenna and see what happens and what kind of a return loss we're going to get as I move the antenna around. And this is going to be a little bit tricky, so let me rearrange this and shoot it again. Okay, let me see if I can do this within any reasonable space that I have here. So here are the two polarization inputs of the antenna. Let's go ahead and connect to one of them and see what happens to the waveform. Let's connect to the top one. There we go. And check it out. We have indeed some response indicating possibly around the frequency we want. And remember, this antenna is sitting on my table. There's a lot of things in near field next to it because the frequency is pretty low. So, it's not in its ideal environment. There's a bunch of stuff around. So if I go ahead and pick it up and I move it around, you can see that you can totally change the response. And right now it seems to have a fairly good response. I'm pointing it upwards toward the ceiling. So let's go ahead and move the marker. If I can. Sorry, I don't want to block the screen. I only have two hands here. So here we go. There it is. Check it out. Right there, right in the middle of the band, exactly where the diplexer is centered. So it is working quite well. If I rotate it around, you can see I can change the response quite drastically. If I put my hand on it, at some point in some configuration, I can totally destroy the response by blocking. There it is. Like you can see right now, I'm just killing it because I'm totally changing the impedance of the antenna by doing so. But by removing it, I got minus 16, minus 17 dB. Return loss is not all that terrible there. So let me zoom in here so you can see what I'm talking about. Yeah, so it looks pretty good. Let me move it around again. Get a better response there. There you can clearly see that indeed we have exactly what we would expect it to do. To have a return loss that matches the diplexer. So this routine that I'm doing with using an external directional coupler, obviously Siglent has their own directional coupler, and you can put it in a routine and give you a proper return loss curve. But this is essentially what's happening inside the instrument, so you can get an idea of what's going on and how easy it is to measure return loss of this antenna. So now using the instrument, we have essentially fully characterized at least some major components or major performance of the diplexer as well as the antenna to make sure they are in the right frequency range, they match each other. Obviously, there's a ton more measurements you need to do in a system like this. We're not getting full vector return loss here, which a spectrum analyzer cannot give you. But nonetheless, it's a pretty good instrument for doing these type of measurements. So let's go ahead and do some other little measurements here and there. Take a look at some of more of its capabilities just to familiarize ourselves with the software, and that would be it. Now, one little thing I forgot to mention is that this instrument has a mode directly for reflection measurement, which I just did with the antenna using a manual mode, where I did it myself and normalized the tracking generator. But you could also use the built-in procedure that's into the instrument, and it's basically doing the same thing. You can do a cal open, which is basically what we did, and then you can do your measurement afterwards, and it just gives you a different user interface, more similar to what you would get from a magnitude measurement of a S11, let's say, on a network analyzer. So you can also use this, but I just prefer doing that myself using the normal traces, but it's nice to see that it is also built into the unit like this. So the Siglent SSA also boasts to have a very good resolution bandwidth, all the way down to 10 Hz. And this allows you to discern tones that are very close to each other. It can be very helpful if you want to catch periodic signals, and I've talked about that before. So let's go and see what it looks like right now. So right now I'm looking at a 1 GHz tone. If I do a peak search, you can see it's around 1 GHz, and then we can go ahead and look at it a little bit closer and see what it looks like. So here's 1 GHz. Let's go ahead and reduce the span continuously. And right now at 5 megahertz, let's keep going. Let's keep going. This is 50 kilohertz. Now it is 20 kilohertz. And now I'm beginning to see something. 5 kilohertz, 2 kilohertz. Now if I go to 1 kilohertz here, I'm going to have to move the center frequency because these are not locked to each other. These two devices, these two instruments, and there it is. And check it out, we are indeed able to discern tones that are very close to each other. So I can go under bandwidth, and we are at 10 Hertz resolution bandwidth, and we can see very nice dynamic range on these tones, which are only 50 Hertz or 100 Hertz apart. Let's find out. Go under the marker there, and do a peak search, and then we can turn on peak table. And it tells us all the different peak signals it is catching, and they're very, very close together indeed. And if I look very close to here, you can see that they are exactly 100 Hertz apart. So it has no problem capturing very, very small signals here. So right now we have a total span of 1 kilohertz and a resolution bandwidth of 10 Hertz and a video bandwidth of 10 Hertz, and the sweep time is about 250 milliseconds or so, which is not bad. It's reasonable, and you can see it does a very good job detecting these tones that are very close to each other. This can be pretty handy when you're looking for those troublesome spurious tones that are really close to your carrier. So let's look at some of the other capabilities built into the unit itself. So let's go to a center frequency of 1 gigahertz once again. And let's reduce our span so we can get our main tone here in view at a 50 megahertz span there. So right now there is no modulation on top of this tone. I'm going to go ahead and enable a 64 QAM modulation with a root raised cosine coefficient of 0.5 directly on this carrier. So I'm going to go ahead and turn that on, and there it is. We can see our waveform quite nicely. Let's go ahead under the measurement functionality here. We can see a whole bunch of different applications built into it. Let's look at the spectrum monitor here, which is very classic waterfall intensity grading. We can see the active area of our spectrum there where the signal is occupying. Now I can go ahead and, for example, change our data rate, and we can capture that by seeing the difference there. So I'm going to go under my carrier setup here, and instead of 10 megasymbols per second, I'm going to send 1 megasymbols per second. And you can see it's going to occupy less bandwidth, and this is reflected very quickly on our waterfall display here. Now, the rate in which this waterfall flows obviously not going to be very fast because this is not a real-time spectrum analyzer, but it can be very handy for capturing various effects. I wish it was a little bit faster, but it is doing a lot of computation, so it's hard to catch spurious events or one-time events. It's just more likely to just useful for showing you a trend. So let me go ahead and put it to 10 megasymbols per second. Again, you can see the spectrum getting wide again, and you can see that. So very nice there. So what about some of the other features? Well, you can also measure occupied bandwidth. And it does a very good job. It's very quick in this mode. So 99% of the power is being captured within a 13 megahertz bandwidth. Now I can go ahead and change my root raised cosine coefficient of the pulse shaping I have on the QAM constellation. I can change that from 0.5 to 0.1, and that's going to shrink our bandwidth. It's going to be getting closer and closer to the Nyquist, and pressing that, you can see that indeed it does that, and the occupied bandwidth is now 10 megahertz, very close to the 10 megasymbols per second that we are sending, very close to the Nyquist limit. So looks very good, does a very good job there. I can do an adjacent channel power ratio there, and I can do under measurement setup, I can define my channel. So let's say my main channel, let me just increase my adjacent channels. Let's say, let's move them a little bit farther apart. By the way, look how easy it is to control Look how easy it is to make these adjustments. I'm very happy with that. So let's say my channel is about around here, and my main channel is occupying the entire bandwidth over here. So now it gives you very nice measurements. You can see, my main channel has about 0 dBm of transmit power, which is correct. My left and right channel about minus 37, minus 38 dBm. So we have about 40 dBc or 37 dBc of adjacent channel power ratio. It gives you all the information there. This is very handy when you're trying to find nonlinearities or out of band emissions and so on. But of course, again, the EXG is a very clean source, so we don't have a lot of out of band problems there. So it works really nicely as well. If I go under over here, and then the channel power is obviously just a subset of the adjacent channel power ratio, because you can get that measurement very easily there as well. Or you can actually do a TOI measurement. Now, obviously, TOI is not going to work on a QAM constellation, so let me change that. Let's go under mode here on my EXG. Let's turn off the digital modulation there, and let's go do a two-tone. If I can get to that menu here, and here's our two-tone, and we can turn that on, and there's our two-tone there. Let me reduce my span so it can capture those. There it is. The span has been reduced. Let me reduce the resolution bandwidth. This thing is so linear, it's hard to actually capture the TOI. There it is. I can see some carrier leakage in the middle there. You can see the skirts of the phase noise of this instrument. Again, this is the phase noise of the SSA, not the phase noise of the EXG. And we have very clearly, nicely marked regions where the TOI is being detected. So the lower and upper TOI frequencies are given, the power is given, and we have about 30 dBm of the third order intercept coming from the EXG, which is to be expected. EXG is an extremely linear arbitrary waveform generator and a modulator built into it. So it does a very good job, and these little functions that are built into it, they may seem straightforward, but the ease of use and the fact that they give you measurement very quickly, I'm pretty happy with that. And the screen real estate usage isn't fantastic. They should be able to adjust that. For example, if I go under channel power, I mean, there's no reason for all of this empty space. They should just move this down. I understand why they've done it this way, because they only have to then program the GUI for certain sizes. It doesn't have to be scalable and so on, which makes it more complicated. But it's just such a waste here, because for channel power, you don't have anything else to display. You're just wasting valuable area. But other than that, pretty good. I'm pretty happy with it. And let's see what else we can do with this. Let's take a look at the Easy Spectrum software, which is the remote interface software for the instrument. I tried to get it to work with USB. It just kept crashing. So I ended up connecting it through the Ethernet port, and I've just assigned an IP address to it, connected to my router, and I can define a Visa interface and very easily connect to it and do a remote monitor. And you can see it's very fast and responsive. Right now I have the instrument connected to an antenna, so it's monitoring all kind of RF activities around my house. Here you can see a bunch of signals coming and going. These are all the ISM bands and the Ethernet and Wi-Fi and Zigbee and so on, going Wi-Fi happening around here. And there's some constant frequency over here. I'm not sure where this is from at the moment. And I can go and do a peak search. There it is, and you can see it's catching this peak because this peak at the time was larger, and I can go continuous peak, and it will then jump back and forth whenever there is strong activities here for my Wi-Fi. So it's going to jump back and forth. Let's turn that off for a second, and let's do a couple of peaks until I catch the this one right over here. Now that we have this, let's go to center frequency there, and now I can go under frequency, and I can change my span to 200 megahertz. And go to 100 megahertz. There it is, and you can see, very nice. You can see the various activities coming and going. It's got a fairly quick sweep here, as you can see, very responsive through the Ethernet port as to be expected. And I can do all the measurements here. I can go ahead and enable different measurements that we saw, but I also have a 3D spectrum monitor here. And there we go. You can see a nice 3D view of these waveforms coming and going, different packets and different activities. So you can see it's nice. It's obviously not available on the instrument, most likely because of its computational intensity. You cannot have this to be there. But yeah, other than that, very nice and straightforward GUI interface, similar to what's essentially on the instrument. Now, one other thing you can do is you can do an entire EMI software that's built into it. You can play around with that. I'm not going to go into details of this right now because this video is already pretty long. I'm going to leave this for some other time, for some other experiments, and maybe a repair or something where we're working on that, and I'll show you that as well. But just know that it also exists. And there you have it, a complete review teardown of the Siglent SSA, and I hope you enjoyed it. As always, the best way to support me is through Patreon. A link will be in the description. I'm almost at the second goal that I have set in Patreon, and the Patreon supporters are the reason why I can do more advanced repairs and buy more expensive equipment from eBay. And you can always like the video and leave a comment on it. You can also let different vendors know that if you value my reviews and then if they are part of your decision making to purchase something. I don't get any part of the sale of any of the equipment. This is just so I can have a good relationship with them and continue to be able to bring you equipment to review and tear down and so on, which I'm sure everybody enjoys. So I hope you like this. I'll see you in the comment section. Until next time.